Theoretical physics has been stalled for nearly a century by a strict mathematical contradiction. General relativity is defined by the smooth, continuous geometry of spacetime. On the other side, quantum field theory requires discrete, jagged probability states. The two systems do not overlap without generating mathematically uncomputable errors. Frameworks like string theory attempt to resolve this friction by mathematical smoothing. However, achieving that math requires compactified extra dimensions, which ultimately results in a sprawling landscape of arbitrary parameters and a complete loss of predictive falsifiability. Moving past this impasse requires discarding a long-held assumption, the idea that mathematical infinity is an error that must be renormalized or smoothed away. Instead, the framework we are examining treats infinity exactly as classical philosophy first envisioned it. Infinity is a strict structural ontological primitive. This model posits that stable physical existence is carved out of an infinite, undifferentiated substrate by a generative symmetry constraint, resulting in a stable, finite knot of existence. This system is formalized as the theory of infinity. It operates on the mathematical principle of creatio ex totalitate, creation out of totality. This diagram maps the triad. First is psi, the infinite substrate, representing boundless potential. Second is phi, the generative constraint, acting as the active principle of order to shatter primordial symmetry. This creates theta, the emergent finite, our observable universe, a stable topological knot. This structure relies on co-inductive numbers and not infinity. A physical knot reaches a final stable state only after continual mathematical refinement, filtering away noisy details until only the scale invariant structure remains. The systems that endure this refinement process are persistently governed by the golden ratio. Kolmogorov-Arnold-Moser theory demonstrates that because the golden ratio's continued fraction expansion consists entirely of ones, it is formally the most difficult number to approximate. It provides maximal resistance against resonant perturbations. Physical existence becomes structurally equivalent to mathematical self-consistency. The observable universe acts as the greatest fixed point of a monotone operator, settling into the exact state capable of enduring the friction of infinity. To audit the precise mathematical intersections where a continuous manifold collides with discrete integer boundaries, the system executes a rigorous verification methodology called the friction versus fiction protocol. The protocol relies on apathetic decompilation. We deploy Monte Carlo accumulators as analog Diophantine solvers. By sampling finite topological sets through cumulative time averages, we isolate the exact continuous geometric mass of a localized space. We establish a baseline test, applying a standard one-dimensional linear statistical model to draw uniformly from a localized Fibonacci boundary set. This chart demonstrates the result. The continuous statistical model fails due to topological phase drag. The dense golden lattice pulls the expected mean downward. Notice how the continuous tracking lags behind the discrete integer anchors, leaving a gap of approximately 0.018. In standard physics, a 0.018 gap is routinely discarded as an algorithmic rounding error. The friction versus fiction protocol formally classifies the specific residual as thermodynamic exhaust. This logarithmic residual is the exact topological footprint of surviving Brownian motion. It represents the literal physical heat required to compute an infinite continuous boundary within a finite state random walk. To calculate pure structural invariance, the system must bypass cancellation errors and topological phase drag inherent in one-dimensional linear statistics. The framework executes a structural computational upgrade via the L2 Euclidean norm lift. This commands the stochastic Monte Carlo accumulator to evaluate the squares of the random variables. Because the golden lattice grows exponentially, squaring the integers causes the upper boundaries to expand at a greater rate than the lower ones. This process effectively isolates the higher-order signal while burying the linear probabilistic noise. This operation constructs a topological high-pass filter, or quadratic ergodic sieve, stripping the linear phase drag out of the mathematics entirely. By taking the ratio of adjacent empirical masses extracted from this squared space, the empirical output converges to the exact pure golden ratio. This synthesizes the theorem of topological ergodicity. Within a closed golden set, macroscopic accumulations are physically forced by the intrinsic geometric mass of integers to orbit the structural invariant. The discrete universe strictly fills a predefined topological mold rather than yielding to unconstrained chaos. We can now pivot from evaluating static limits to analyzing the derivative spaces of three-dimensional Fibonacci polynomials, asking exactly how this abstract golden geometry maps to physical interdimensional space. The distinct continuous limit rails governing these geometric spaces are exposed by executing a specific mathematical mechanism, the differential calculus drop. This graphic maps a baseline two-dimensional test. We apply a standard 4-3-2-1 differential operator to a generic fourth-degree Fibonacci polynomial embedding. By applying Vieta's formulas, the continuous boundary of this derivative operation outputs a precise geometric limit. The standard derivative operator reduces the dimensional weight of the golden ratio by exactly half. Applying discrete integer derivatives to these polynomial spaces maps the fundamental geometric rules governing the collapse of higher dimensions into lower ones. We initiate the ultimate physical test by subjecting a three-dimensional space to the exact same differential drop to observe the resulting volumetric shear. We apply the identical 4-3-2-1 drop to a three-dimensional Fibonacci polynomial embedded with rung 9 coefficients, 44, 81, 149, and 274. Applying Vieta's formulas to this calculus drop yields an exact discrete product of the roots, the fraction 137 over 88. We begin apophatic decompilation by analyzing the uncut mass in the denominator, the integer 88. The number 88 identifies the 12th rung of the Fibonacci sequence, providing the mathematical address for the specific geometric node. In physics, the standard model is comprised of exactly 12 fundamental fermions, the spin 1/2 particles that constitute all known matter. When we treat this 12-dimensional node as a quantum dyad, applying the spin 1/2 operator, the resulting math fractures the geometric mass. The remaining integer is 137. This integer, 137, matches Pauli's fine structure constant, the electromagnetic constant that governs every atomic interaction in the universe. The observable universe operates as a mechanically sealed matrix. Fractional calculus and interdimensional volumetric shear reveal the exact geometric blueprints of our quantum reality. Infinite space is a tightly wound, perfectly resonant topological knot.